Michael Christen. He is a long-time open source developer with over 20 years of experience building tools for the FOSS community. As a maintainer of YACY, a decentralized search engine, and SUSI AI, an open source conversational AI, he cares about open knowledge and DIY tech. So today he'll be telling us how to practice with self-hosted LLMs and developing LLM agents.
So, hello everybody. This is more a workshop than a talk. So, when I wanted to do this talk, I presented it as workshop, but in the calendar it's now given as a talk. But I want to have it as a workshop. So you can take out your laptop and do coding with me today. I attended some other talks and I've seen a lot of examples where people show how to use LLMs and AI and chat applications in Google Colab. So I wondered a little bit why this is the best example, because this is a cloud application. It's not running on your computer and it's not even free software. So if you are attending at a free software conference, you should take care that everything you are doing is running as free software. And that means on your own device at the first place. So sometimes there is the impression that AI and chat applications and large language models need so powerful hardware that it's of course only possible to do this on a cloud device or using an API. But that's not true. There are so many frameworks and small models and capable models that you can easily run this on your own computer. So if you have 8 gigabytes of RAM on your device, you can run all the examples I will show you, and you don't need a GPU. It's running on CPU, and it's running fast on CPU, and you can do small applications and small example applications. So let's start with the idea what I want to do. The framework we are using is Ollama. Ollama is a framework around Llama CPP. And Llama CPP is the first framework which appeared when the Llama model leaked 2 years ago. So it appeared almost instantly. Within a week, someone coded this kind of client for a large language model, which was published by Meta, not on purpose, but later on purpose. And many more models appeared after this. And there are large repositories for large language models like Hugging Face. And I want to show you how to use this. Yeah, I don't think I need the microphone because in Summits I want to sit down and do some coding, and then I don't have a free hand to use the microphone. So I think we don't need the microphone. So thank you. I hope you can understand me also at the end of the room. The recording is here. I hope this is working. So I also prepared a repository for the example script. So I want to show you how to download the framework for large language models. I want to show you how to download the large language models, not only framework, but also the models itself. And I show you how to download the example scripts we want to try now. So what we are going to do is we go to ollama.com, and I want you to open ollama.com right now and install Ollama right now. And when we have done this, we want to use a model, and what we are using is Llama 3.2. It's a model with 3 billion parameters. So for example, ChatGPT 3.5 was 175 billion parameters. This has only 3 billion parameters, and it's a quantized version with 4-bit quantization. So what does this mean? If you have a model, it's a large number of weights, and these weights are floating point numbers. They have precision usually with 16 bits. But if you want to have a smaller model, you can have the same number of weights, but with less precision. So this is called a quantization. You take the 16-bit precision and remove, for example, 8 bits, then you have an 8-bit precision. And you are losing some intelligence when you're using this model. But it's not a lot. And you can even make this much smaller. You can have a 4-bit precision of the floating point numbers. And it's even with the 4-point precision very capable. This means that a 3 billion parameter model doesn't need 3 gigabytes of memory. In this version of the model, it uses only 2 gigabytes of RAM. That means even if you have only 4 gigabytes on your computer, you can run this. You can run this model on a Raspberry Pi, even on a small Raspberry Pi with only 4 gigabytes of RAM. And that's what we want to do. We want to run software on your own computer, and even on small computers have AI on it. We don't need cloud service. So are you downloading olama.com right now and running it on your own computer? Because we will want to do this now here on my computer. So I show you quickly what happens afterwards. You go to my repository, it's at GitHub, Orbiter LLM RAG cheat sheet. I called it a cheat sheet for AI applications. And I will show this to you later on the web page, and we will do some applications with this. I hope you know how to clone a repository. It should be easy. And then we make the most simple applications, because if you want to use something that you want to understand, so what I do is I start with the most simple program that doesn't use any API if possible. So this is a kind of a hello world application to an API. If you just use the most simple thing to access an API, and that's a curl command. Okay, now let's go step by step through all the things we need to do this. So first thing is, yes, olama.com. So I think you don't need to sign in. You don't need to sign in. Just click on download and use the framework for your own computer. And what happens then is that you get, can you read this? So Olama is not an application with a graphical user interface. It has a command line interface. And it works like this. You type Olama and then a command. So for example, if you have downloaded models, you write Olama ls. I have a lot of models already downloaded. And what you want to do to start with my examples is Olama pull Llama 3.2. And because I already downloaded this, it's just looking if I have the latest version, and it's already done because I already have this here. This is Llama 3.2 latest. So how do you know which kind of model you should download if you don't want Llama 3.2 or maybe a more capable one? So on this web page, you have the option to click on models, and then you get a list of models. Here we have, for example, one of the best working models, which is really intelligent, really good, should run on most of your computers, is Phi4 from Microsoft, published as an open source model with a proper open source license, I think. Yeah, it has MIT license. And this model card shows you what you get. And for example, here you have tags. The tags show you which kind of model you get. So you can have a 16-bit precision model, or you can have the 8-bit precision model, or the 4-bit precision model. And There's also the short version to name this. The FIF4 is, like it's documented here, it's the 4-bit precision model if you run this. So you can just click here, copy this to your command line, and then you're downloading the model. Oh no, I'm running the model right now. And you can say hello world. Hello world. And it's running quite fast on my machine. What is FOSS? Let's hope it knows what it is. So another place where you get models is Hugging Face. So these kind of models that Llama CPP, which is the engine behind Ollama, is running are so-called GGUF files. And if you click on models on Hugging Face, you get the list of models sorted by most popular right now. And I like to do filter with GGUF, so I get only GGUF encoded models. So let's see, maybe you want to have Gemma free 1B, like this. The model files are in files and versions. Here you can see how large they are. So the 4-bit quantized version is under 1 gigabyte. And if you want to install this, you click on use this model right here. There's the option Ollama. You click on Ollama. You get again an option to select the quantization version you want to have. You just click copy, and that will run the full method and run method to run this on your own computer. So you can always keep up with the latest models which are published. You see which one is most popular and so on. So you have access to a large set of good working models. You know that they are open source and you can use this in your own application on your own computer. So let's see how to actually do this. And I want to suggest that you download or clone my repository with the examples for it. So you go to GitHub, to my account, which is Orbiter. No, that's me. And I prepared a repository here. So you just click on the LLM RAC cheat sheet, and copy the code by using this link to clone it. Okay? Are you on it? Do you need more information? Okay. So let's see what we have there. So I open Visual Studio Code where I have cloned this repository. Is this big enough? Maybe this is a bit better. Okay. And in the API example folder, I have named these files in such a way that the order of the lexicographic order of the files is also the right order to try them out. Okay? So we will try them out from top to bottom. So the first example that we try out is a simple hello world like application with a curl command. So we could run this, but at this time we want to just copy the curl command and run this. So what is this? A lot of things we see here that comes out. This shows us how the chat API works exactly. So if you have a chat front end, you see that the tokens appear one after each other. And that's what the API does, is it puts out single lines beginning with data, and then there's a JSON. And within that JSON, there's one string which contains the token. Here's a token in content. I'm just a computer program, so and so on. So that's the answer that the LLM gives. And if you want to have a front end rendering this content, you have to read this line by line, pass the JSON, and present the content of that string. So that's not the most proper way to use it in a kind of application, because this is for presentation. So the second example I have here is to use the API, but without the stream. So I have here the option stream true. And the next example is the same thing, just with stream false. So how does it look if we make this with stream false? Okay, so this is a mess. It's not really printed in a very way. So therefore, I made this command to run this through a pretty printer with JSON, with Python. This is a Python pretty printer, pretty printing the JSON output from the curl command. Okay, and this is much better to process in a client application. So you have a lot of attributes, and this is not a Ollama typical response. This is the same API which OpenAI publishes. So you can change the endpoint address of the server you're using to OpenAI, and all the other services, all the cloud services use the same API. So what we are watching right now is exactly what comes out of these APIs. So we know how to write client applications which are handling this kind of output. So it outputs a choices object which has some detailed information with an index number, a message. It says the message has the role assistant, which is the answer from the AI, and it has a content, and that has a string. I'm just a computer program. What's happening right now? Why is it shutting off? Okay. Is this working? Okay. Okay. So the next step is that we want to use Python. So it's easier to integrate all of this. This is the Python client application. If you just want to have an HTTP client connection using just basic libraries, so no fancy libraries, just the basic libraries. And if you run this, we surprise get the same result because we just output what the API is delivering to us, but we use Python, not curl. So the next thing would be that we say, okay, is there a library which makes it easier to access this API? And this is, of course, LangChain. LangChain is showed here in many presentations. So the program gets a little bit smaller and it's a little bit more easier to understand. So I just use a special client version of LangChain, which is called Chatolama. And this is using the actual special endpoint from Ollama, because they have their own API, which is not compliant to OpenAI. And this is using that client application. So if we run this, it extracts only the message. So if you print the response content, we just get the string of the response. Okay, so now we can do many things with this output. So what kind of applications can we think of where we integrate this kind of LLM output? So let's see. I have some more examples. So there's a concept in the transformer construction. If we run a context through the transformer, then we have at the end of the transformer embeddings, which represents tokens. And the transformer always selects that one token, which is the most likely one. But in some applications, we want to have a regular expression saying, okay, the shape of the output should be conform to what we want. We want to define a specific shape, so we don't take the most likely output, but we take that output which fits into our regular expression and is the most likely one. And the use case is that we want to have JSON. So if we want to have JSON, we could just write in our request, write your answer as JSON, but it doesn't define how the JSON is constructed. So if we run this, we of course get an output. It says translate the user sentence to German, and the user sentence is I love programming, and the response is Ich liebe Programmieren. Okay, that's the sentence. But what kind of JSON is this? So this is the whole thing is JSON. The content of the response is JSON, but it's a string encoded JSON. It's a so you have that kind of meta symbols to quote, and so on. And it's not, it is JSON, but we don't know what kind of format is that. So a parser wouldn't say, I don't know the attribute names. What can we do? We can say format JSON. That means we do not only formulate that the output should be JSON, because then the LLM can still decide that it is kind and say, of course, I want to output JSON, and here's the JSON, but we don't know if there's JSON somewhere. We have to search for it. And if we put this format JSON inside, then everything must be JSON. But we still don't know how this is formatted. So let's do this. Okay, now the translation, liebe Programmierung, has a key. Yeah, it's called EN. But did we expect this? So we don't know. We can hope that there's a property named EN, but doesn't make sense. So we want to give it a specific shape. So the specific shape can be declared in the format argument. And this will create a regular expression inside of the Olama application, which tells the transformer that from the most likely output, there must be something which is according to a regular expression, according to these properties. So we want to have a multi translation option with the keywords English, German, Spanish, Italian. So okay, now we run this also through the formatting. Okay, the formatting shows us how this looks like. The content gets JSON formatted string in JSON with the attributes German, Spanish, Italian. Yeah, Spanish, Italian, German, and it has it made 3 translations out of 4, because I can set a required string and containing German and Spanish. So the regular expression requires that these keys appear, and the LLM decides to make 3 out of it. It can be 4, but you have the option to set required to only a subset of what you want to have, because sometimes this makes sense. How much time do I have? Okay. So of course now we do this in Python again. Okay. So this is the Python version, and we read out the JSON, and the JSON is then not JSON formatted JSON, but simply JSON, and I get this kind of output. And now I can use the result of an LLM in a programmatical way, because I've structured data coming out of an LLM, which is very nice to have. I know exactly what kind of shape it has, so I can create real applications. I can create large data extraction routines. Yeah. So if an LLM model is like a compressed data file. If you have seen my presentation from yesterday, the outcome from the presentation, how does it work completely, is that an LLM is nothing more than a very strongly compressed data file, okay, with some strange attributes, but it's like compressed data. And if you want to decompress something, you can write a loop around some kind of extraction rules, and you can extract a large amount of data, and it's in a structured form because you can say what kind of structure should it have, and you get structured data out of it, so it can process that data. Okay. So the next version of this iteration of different versions to extract data is, of course, to use LangChain. So the program is not so much different. This is HTTP, this is LangChain. Okay. So same, but different. So if you say, why isn't he using LangChain? This is so easy. So you have the example, but I personally like to not use a library because then I understand in a more detailed way how it works, and you don't have so many dependencies. And the difference is not so big. Yeah, it makes it a little bit more convenient, but not so much that I would say this is what I really want to depend on. Because especially LangChain is changing the API all the time. It's a big mess. You have to change your imports, and so it's a bit strange. So the next example is that we want to create a classifier. Classifier is one application that is neat to have. So my example here is I create a mood classifier. Okay. And for the mood classifier, I declare that the attributes of my output is not a string or an integer, but the type is literal, which means I can assign an enumeration of specific words that I want to have as an output. Okay, and the mood classification has three options: surprise, angry, happy. So these are the three classes that the LLM may output. It doesn't have the choice to do something else. It can only use these three words. So therefore, I can pass the output and say I classified something that I put inside. So here is my typical access rules for the LLM, Chat Ulama, and I have three sentences that I want to classify. I love programming. I hate programming. I found a solution, and it outputs the classes of the emotions behind this. So I love programming is happy. I hate programming is angry. I found the solution is surprised. Okay. So now we also found an answer to the questions: can AI have emotions? Yes, here's the example. AI can have emotions. It's very simple. So we can use this now in a real application where we say, let's have a chat with an LLM, but the LLM should recognize my mood and respond in a specific way according to that mood. And how do we do this? We always have a system prompt. The system prompt defines how the LLM should answer on a question. Should it be polite, or should it be more scientific? Should it think more, and so on? So now we define how it should respond accordingly to these moods. Okay. So I have the same classifier here. I have surprised, angry, happy, and I have different system prompts that I define here for the option that the user has a happy mood, a surprised mood, and an angry mood. If If you are angry, then it says team up with the user to eliminate the program, destroy the source of anger. So the idea here is that the LLM is really emotional. It's reflecting your emotions in the strongest way. Okay. And if you're happy, then be extremely excited. Yeah. And so on. So I have the same prompts. I love programming. I hate programming. I lost all my data. It's a little bit different. So how should it respond? So what it does here is it's a two-step answer. First step is identify the emotions with the classifier. Second step is use the emotion with the system prompt, and then do the answer with that system prompt. So it takes a little bit longer because it's free time. 3 times it must do the classification. So first answer is I love programming. Oh my code, I'm so excited for you. Programming is amazing. Second thing, I hate programming. A big hug. Okay, let's take a deep breath together and so on. And I lost all my data. Let's calm down. So okay. So this is a funny example that shows you that you can use LLMs in a very different way. It's very easy to create a classifier, and you're still far away from big libraries. You don't need a server farm for this. It runs on all your computers that you have. Okay. So that we know how to use the system prompt to tell the LLM more than it knew before. We can use this to extract information from somewhere else and use that information from somewhere else to create answers. So what we do right now is that we take a public available file, a large file with some strange information inside. And I was thinking about what kind of example can I use? And what I'm using is the jargon file. So maybe you know the jargon file, it declares all the strange terms that you can have as a programmer. Some of them are very outdated and maybe not used anymore. So the idea is that using information from the jargon file creates a different answer than not using the information from the jargon file. And this applies especially if you have a very small model, because if you have a very small model, then it doesn't know all the world's information. It maybe just knows the most important world information, and the most important is defined by the team that trained the model. So you don't know what they thought is most important. But if you have some information where you think this is for you important, you can put it on top of the model file. And this is in some kind a piece of task you have to do for retrieval augmented generation. So RAG is, I heard this in many talks here. What is RAG? RAG is that usually you create a proxy, and the proxy sits between the LLM and your client. The proxy extracts data from a search engine from somewhere else and presents this to the LLM in some way, which is usually not very well documented. You can do this in different styles. For example, you can put it in the system prompt, or you can use it in the user prompt as an addition. With a text like, maybe you could use the following data and then attach the data. So the first step we do here is that we use LangChain to read the file and split it into smaller pieces, because the jargon file is a large one. So if you want to run this example, you need to run this wget in advance, because it takes the jargon file from Project Gutenberg, a place where the texts are published that are available with yeah, it's not a free license in the way that it handles licenses, because from a lawful perspective, very old texts are outside of the copyright scheme. For example, as far as I don't know, I don't know if this is precise and correct, 65 years after death of the author, I believe this is correct. Or if the file is published under a public license or free license. So I think we can do this with the jargon file. And the first task we have to do here is read it. We use the library text loader for the file. And then we need a text splitter. And the text splitter can have options. For example, here you define that it has a specific chunk size and how deeply they overlap, and where it should separate. So it should separate only at line ends. And then you have a search engine at Retriever. Mostly people show here how to use embeddings and how to use a vector search. A vector search is using the embeddings, that means the meaning that an LLM does see, to find matchings. But from my experience, this is not working so good all the time, and it's especially not working good in other languages than the one which was used to create the tokenizer. So if you have, for example, the German language, German has a lot of connected words. You can have very, very large words which have a connection of different other words, and the complete long word has a completely different meaning. So if we take this apart into tokens, the tokens doesn't have the meaning of the word, and therefore the search with a vector search doesn't work so good. Therefore, I used a different kind of indexing, which is here the TF-IDF retriever. So this is also a search, but it uses the same ranking like Lucene is using, this the term frequency and inverse document frequency ranking. So it's acting like a standard search engine. So it's like all the other indexing services outside of vector search are working. And so I make one search request, and the question is, what does Wombat mean? Okay. Wombat. Hey, I get an okay. So now I get 2 fragments. Because I asked for two fragments, therefore I get 2 fragments. And what I wanted to have as a result is this one. The first one doesn't apply so much. And now it's according to the LLM to decide which should it use. And so the application to use that response is that I have the same content I load, I have the same question, and I have 2 outputs, one from the LLM request without the context from the search, and another one with the context of the search. Okay. I use a different model. I use Phi4 here because the Llama 3.2 was too stupid to use the context. So sometimes the model is too small for your task. You have to use a bigger one. Time is out in 5 minutes, or but I can see this without my glasses. Sorry. Time's up. Let's just run this so we can see the result. Okay. So with context, the answer is wombat is an animal in Australia, and the second answer is it's an acronym for waste of money, brains, and time, which we get out of the Dragonfly. So thank you for listening, and I hope this is useful for you.